Matters in both liquid and gaseous states are considered fluid. Generally, fluid does not have definite shape. Instead, it follows the shape of container. Liquid has definite volume, and this is not the case for gas. Knowing the amount of molecules and the resultant mass is certain, the mass density of fluid may change with temperature and pressure. For instance, the density of water at 4 degrees Celsius under atmospheric pressure is 1000 kg per cubic meter, and it decreases with either increasing or decreasing temperature. A fun fact, the density of ice is less than water. Therefore, we can notice an ice cube floats when it submerges in water. The variation of mass density is significant in gas. Ideal gas law may be applied to determine its mass density under certain temperature and pressure. For air, we may take the gas constants R as 287 Nm per kilogram per Kelvin. For instance, the mass density of air at 20 degrees Celsius under atmospheric pressure is 1.204 kg per cubic meter. The change in volume with temperature and pressure is nearly negligible for liquid. On the other hand, such change is significant for gas. When subjected to pressure, the volume of fluid decreases as the gap between molecules is reduced, and they are now closer to each other. The change in volume under exerted pressure is described using bulk modulus. Bulk modulus is dependent of temperature and pressure, since the state of molecules is dependent of them as well. Bulk modulus of water and gas are usually taken as 2.1 GPa and 103 kPa respectively under normal pressure and temperature. Generally, liquid has high bulk modulus, and this causes the change in volume negligible even if it is under high pressure. For this reason, liquid is usually considered incompressible. On the other hand, gas is always treated as compressible fluid. When subjected to external forces, fluid responds differently from solid. The tensile strength of fluid is zero or negligible if it exists. Compressive strength exists in fluid if and only if the fluid boundary is fully restrained, which usually takes place when it is inside a container. When subjected to shear force, the fluid layers displace and causes the fluid to deform continuously as long as the force presents. Most fluids are Newtonian as they obey the Newton's law of viscosity. Based on the law, the shear stress between adjacent fluid layers is proportional to shear strain rate. It shows a linear relationship, and the gradient of stress against strain rate curve is known as dynamic viscosity, or simply viscosity. Fluid with high viscosity does not flow easily, as the shear resistance between layers is high. We also have kinematic viscosity, which is a ratio of dynamic viscosity to fluid density. We may also find non-Newtonian fluid, where the correlation between shear stress and shear strain rate is non-linear. We call such fluid dilatant when its viscosity increases with shear strain rate. The harder we push a dilatant fluid, the greater its resistance against the flow. Non-Newtonian fluid behaves in the opposite way is called pseudoplastic fluid. For this kind of fluid, the harder we push, the faster it flows. Nonetheless, in fluid mechanics, we always deal with Newtonian fluid. Here we conclude our introduction to the fluid properties. At the end of this video, we would like to share some properties of water and air. Thank you for watching. If you find this video helpful, please share it with your friends. We will see you guys soon. Goodbye.